Hey Chem 240, this is the fourth and final video that we're going to do for chapter 19, which is on thermochemistry. So the first thing that we're going to start with is a really cool equation that relates delta G under any conditions to delta G under the standard conditions. So all you have to do to find out delta G under conditions that are non-standard is calculate delta G under the standard conditions for a particular chemical reaction, which you could do from the tables in the back of the book, and then add on RT times the ln of Q, and we'll talk about Q in a second. The R that you need to use is the energy R, 8.31 joules per mole Kelvin, and obviously all the temperatures have to be in Kelvin. Delta G here stands for the free energy under any conditions of pressure and concentration. Delta G0 stands for the free energy at standard conditions. So that means that all the partial pressures of different substances are at 1 atmosphere, and all the initial concentrations that you start the reaction are at 1 molar. Okay? Q is called the reaction quotient. And if you remember back from chapter 15, the reaction quotient takes the same exact mathematical form as the equilibrium constant. You take, if you look at our reaction, A plus 2B goes to C, as long as, let's say, these are molar concentrations in solution, then you would take the initial concentration of the products to whatever power they have. So this is squared, so that's why this is squared. And the reactants go in the denominator, and again, you raise them to whatever power they're at. So A, the coefficient is 1, so that makes this 1 here. And this is 2 because this is 2 in this case. So products over reactants where the coefficients become the exponents. So these are initial concentrations in molarity. If we were doing this for a gas phase reaction, this would be the partial pressure of C squared divided by the partial pressure of B squared and the partial pressure of A to the first power. So same idea, okay? So these guys are at whatever temperature you happen to be, not necessarily 298, but when you get the numbers from the back of the book, those are at delta G0, which has these conditions, and they're also at 298 Kelvin, okay? And you remember, if you turned out that you were actually at equilibrium, that you were at equilibrium, then two things are going to happen, right? We know that delta G for a chemical reaction, the chemical reaction that we're interested in, if the reaction is at equilibrium, delta G is equal to 0, right? Delta G is equal to negative when the reaction is spontaneous, goes from left to right as written. Delta G would be positive when the forward reaction is non-spontaneous. It doesn't happen, but the back reaction would. And right smack in the middle between spontaneous and non-spontaneous is equilibrium. And that's when delta G is equal to 0. We also know that if you're at equilibrium, then your Q isn't Q anymore. These must be at equilibrium concentrations. So Q becomes K, and these things go from parentheses with a little 0, which means whatever concentration you happen to have, to the equilibrium concentration, which has the special case of putting everything in brackets, right? Whatever it is that you're talking about in brackets. That means molar concentration at equilibrium. Okay, now look what happens. Take our equation from above. Plug in a 0 over here. So I have 0, right, because I'm at equilibrium. And then my Q then, because I'm at equilibrium, becomes K. So switch this for 0 and switch this for K, and we have a really cool little equation that says 0 is equal to delta G0 plus RT ln of Q. So what does that do? That would relate delta G0 that you got from the back of the table to K, the equilibrium constants. But what we're going to do is we don't want to have that with zeros. We would rearrange that and move all this stuff over to the other side. And when I do that math down here, plug in a 0 for delta G, switch from Q to K, I get 0 is equal to delta G0 plus RT ln of Q, and all I would do is just bring this over to the other side. So very cool. The delta G0 for any chemical reaction is equal to minus RT, the natural log of the equilibrium constant. So if you know the equilibrium constant, you can calculate delta G zero from it, or if you know delta G zero from the tables, you can calculate what the equilibrium constant is. Okay? If you want to switch this to the log form, which you don't have to, you can just keep it as ln. That's my suggestion because you guys have calculators that have ln. Remember, all you have to do if you want to do the log base 10 is add the 2.3. That always happens. Okay? So here, going back to this really cool equation up here, this is in the natural log form. If you wanted to see that original equation, here's the ln form. But for you guys, I would suggest using this one and this one. Okay. Let's take an example. So for the following reaction, I have calcium carbonate solid in equilibrium with calcium oxide solid and carbon dioxide. So if I heat up calcium carbonate in a closed chamber and I let the carbon dioxide build up, this reaction will eventually come to equilibrium. Okay? And actually, I don't even have to heat it up. I just have to wait long enough. So here it is. I have an equilibrium. I have some calcium carbonate and some calcium oxide. I put them in initially. Their amounts really don't matter as long as they're there because they're in the condensed phase, right? Solids don't matter. So this guy would have a really interesting equilibrium constant. I would take products over reactants, coefficients become the exponents, leave solids and liquid water out. So this is out, this is out. So I would have K is just equal to the concentration of CO2, but it would be more appropriate to use Kp because I'm dealing with gases. So Kp would be equal to P of CO2, so the partial pressure of carbon dioxide. Okay, now delta G zero for this reaction, if I do the reaction, and obviously the zero means that this partial pressure must be at 1 atmosphere. So what is delta G? When you run this reaction with 1 atmosphere of pressure up here, that's the standard conditions. Excuse me, what is delta H? Delta H would be 178.3 kilojoules per mole. Okay, so delta H is a positive number. This is an endothermic reaction. Okay, this delta H, remember, is going to come out in kilojoules. Delta S for this chemical reaction is going to be positive. That's what we'd expect because we make 1 mole of product and there's no moles of 1 mole of gaseous product when there's no moles of gaseous reactants. Plus, we're decomposing something. One thing is breaking up into 2 things. So I would expect delta S to be positive for this to be moving towards more randomness, right? More disorganization. That's what delta S positive is. So remember, when we get this special case of endothermic but positive entropy, we can take a chemical reaction that's not spontaneous and heat it up because we'll make the delta S portion of the Gibbs-Helmholtz equation more important at higher temperature, right? We know that delta G, under any conditions, including these standard conditions, delta G is equal to delta H minus T delta S. So the higher the temperature is, the more I can exaggerate that second term so that eventually it can bring down the delta H and make delta G equal to negative. So that's what we're going to see. We're expecting this to become spontaneous at high temperatures whenever we have both positives, right? That's something you do need to know. Okay, this guy, remember, is going to come out in joules. All right, so here's the question. At what temperature will this reaction that right now is non-spontaneous become spontaneous? Okay, how do I know it's spontaneous? If I looked it up, the delta G turns out would also be positive under these conditions, okay, because I'm not at a high enough temperature, okay? Where did I get these? I could calculate this one or this one from the tables in the back of the book, which would be the delta H0 of formation tables, where I'd look this guy up times 1, look this guy up times 1, look this guy up times 1, and then take products minus reactants. I could do that for this, I could do that for this, and actually I could also do it for delta G0, okay? All right, now really cool. At what temperature will this reaction come to equilibrium under standard conditions? So what do? I take my Gibbs-Helmholtz equation, which says, because it's at standard conditions, delta G0 is equal to delta H0 minus T delta S. Now I know when I'm at equilibrium, even equilibrium at standard conditions, equilibrium means delta G equal to 0. So plug this 0 into here. Now look what I have. I have delta H, I have delta S. The only thing I don't have is T. So to solve this second equation right here, for T, all I have to do is bring delta H over to the other side, right? Or actually, let me bring T delta S over to the other side so it'll be positive. So I have T delta S is equal to delta H, right? T delta S is equal to delta H. How do I get T by itself? Divide both sides by delta S. And I have this really cool equation that says that the equilibrium temperature for a chemical reaction that is not necessarily at equilibrium all the time or can be brought to equilibrium is equal to delta H0 over delta S0. So all I have to do is take the ratio of these two numbers, just make sure they're in the right units. It's delta H divided by delta S. So to do that, I should change the top one to joules or the bottom one to kilojoules. Doesn't matter. See what I did? I changed the top one to joules. There's 1,000 joules in each kilojoule. That's what happened to that guy. Okay, look what happens to the units. Joules cancel out with joules, moles cancel out with moles. I get 1 over Kelvin, that's Kelvin. If you do the math, you get 1121 Kelvin, okay? Above 1121 Kelvin, this reaction will become spontaneous. Okay, if you take 273 off of that, I'll tell you what that is in Celsius. That's 1121 minus 273, still very warm. That would be 848 degrees Celsius. So I'll write that in here, 848 degrees Celsius, very warm temperature. When I reach that temperature, this chemical reaction will come to equilibrium with a concentration of 1 mole, 1 atmosphere of CO2 in it. Okay, you can get it to equilibrium at other places, at other temperatures, but not with that amount of carbon dioxide in it. With that amount of carbon dioxide, that's the only temperature where you can get this to reach equilibrium. Now, other thing, we know that there's no such thing as a negative absolute temperature. So this scenario will only work out when both delta H and delta S are positive, like they are in our case, or in an exothermic reaction with a negative enthalpy. In those cases, I would expect my temperature to be a low number, not a high number. This is a high number because I want to drive it to the point where the S beats out the H. That's going to be at high temperatures. That's when it's endothermic and going to more entropy. The flipped case is both negative, is exothermic and less entropy. That one we want minus temperature. If one of these is positive and one of these is negative, like those two other scenarios, there's no such temperature. So be careful for that, right? Be careful for that. I could ask, is there a possible temperature? And the answer would be no, because one's positive and one's negative. There's no temperature at which you can go to reach equilibrium. Okay, all right, this last section, okay, I was one more example at the end, but this is kind of neat. This is the chapter 19 sort of review sheet. So not a bad page to have out. It's page 16 of the chapter 19 notes. Let's go through all the equations. Okay, we know our 3 state functions that we put a lot of credit in are enthalpy, H, free energy, G, and entropy, S. Okay, you can tabulate them all in the same way from the tables in the back of the book by looking up the delta H's of formation and take products minus reactants where the coefficients are multiplied, right? So this is all of the products with their multiplied by their coefficient, sum them up, minus all of the reactants with their coefficients. You do the same exact thing for delta G, okay? The tables you guys have in the back of the book are at 298 Kelvin or 25 degrees C. S is only slightly different. Instead of having delta S0 of formation tables, we actually have the absolute entropy, S0, of, you look them up for the products, look up the S0 of the reactants, multiply in the chemical equation the reactants by their coefficient and the products by their coefficient. But the structure of those 3 formulas is the same. And you guys know the table I'm talking about, okay? You can look up all of the different chemicals and be able to do any chemical reaction that you want. If they're not in the back of your book, I'm sure there's someplace. You could look on the internet or any other tables. Okay, so that's very important, how to do that. Okay, what does this measure? This measures the heat of the reaction at constant pressure. That's called enthalpy. What does this measure? The free energy of the reaction at constant pressure. What does this measure? The change in entropy of the reaction at constant pressure. And what else do we know about that? Those little zeros mean all partial pressures are 1 atmosphere, all concentrations are 1 molar. Okay, a couple of important equations. I might as well start with the basic one first. Under any conditions, no matter what the conditions are in the world, it is always true that delta G is equal to delta H minus T delta S. This is called the Gibbs-Helmholtz equation. It relates enthalpy to entropy to free energy. What is free energy? Free energy is the amount of useful energy that can go on to do mechanical work or biological work or anything that you need to do in your system. Okay, under standard conditions, just add the little zeros. Same exact thing, you're just limiting it to those under those standard conditions, which we know are 1 atmosphere for partial pressures and 1 molar for concentrations. Okay, what happens if you want to know what is delta G under other conditions when you know it under standard conditions? Well, you take the standard value you get from the back of the book plus RT ln of Q. Okay, next thing we said, at equilibrium, delta G, regular delta G becomes 0 and Q becomes K. So this, I get this formula down here. Okay, excuse me, this formula here, right? Regular delta G goes away. All of that stuff goes over to the other side, so it becomes negative, and I get delta G is equal to minus RT ln of Q. This one and this one are not special. They're just the LOG version. If you prefer that, you don't need them. You can do everything with the LN version here. Okay, last thing from the very beginning of the chapter, okay, this is really important. This comes from the second law of thermodynamics, that the change in the internal energy of a system, delta U, that's the other thermodynamic quantity, is Q plus W. This is any kind of Q, any kind of heat, right? We said that under the special conditions of constant pressure, Q becomes QP, bring the work over to the other side in the form of PV work minus P delta V, and we can collapse those two terms, and that's how U is related to H. So you can review that if you want. But this is really all you have to know. Delta U is equal to Q plus W. What kind of work are we talking about? We really are talking about physical work, pushing pistons down, moving things. It's called PV work. PV work at constant pressure, the pressure stays the same, it's the volume that changes. So work for us is minus P delta V, right? When something expands, that is work done by the system. The system's energy should go down. So expand, this is going to be positive. Times a positive, pressure will always be positive. So this whole term will be negative. Well, that makes sense because an expansion is not good for the system. It's good for the surroundings. The system does work on the surroundings, but the system itself loses energy. Its work would be negative. Okay, how about in a contraction? That's when work is done on the system. Delta V would be negative, so a negative times a negative would give you a positive. That's good. When you contract a piston during the chemical reaction, work is done on the system. Okay, here's two neat things. Delta S is in a spontaneous reaction is the delta S of the universe in all spontaneous reactions is greater than Q over T. So the heat of the reaction in any spontaneous reaction divided by the temperature in Kelvin at which it happened to will give you the change in entropy for that system, okay, for that system. And it will always be greater than, delta S will always be greater than that. If you slow the reaction down and go very, very slowly so that you can capture all the work and do the reaction at equilibrium, then delta S then is equal to Q over T at equilibrium. Okay, so the heat of the reaction divided by the temperature, if the reaction is done at equilibrium, reaction is at equilibrium, is delta S. Okay, and we said delta H is Q at constant pressure. Q is the heat of the reaction. The amount of energy that the reaction gives off under constant pressure conditions is its enthalpy. So this last stuff here, these last three, this is review from the thermochemistry from Chem 1. Actually, I should say this one and this one you learned in Chem 1. Everything else is new. You don't really need these two, but not a bad sheet to keep on the side of your, while you take the exam. Okay. All right, one more example. let's practice a little bit. So for the particular chemical reaction I have here, it's called the Born-Haber reaction. I have a nitrogen plus hydrogen. It's a balanced chemical reaction to give you ammonia. Okay, so we think about this usually as a one-way reaction, but listen, anything can be put under the conditions to make it go to equilibrium for the back reaction to, well, I shouldn't say anything, but some reactions can be turned around so that the back reaction becomes important. So if I wanted to calculate from the tables that I would get from the back of the book, this is what you have. You have delta H0 formation, delta G0 formation, and absolute entropies of all of these chemical species. Okay, so you would just look them up. Okay, so what do? Let's do delta H of the reaction first. I need the delta H from the table for the products, so I need 2 times ammonia. So I grab the ammonia number, and I'm doing delta H, so that's why that's minus 45. Why the 2? Because the coefficient is 2. So products minus reactants. Now the interesting thing with delta H is these two things are elements, right? In their natural form. That's the way you would ordinarily find nitrogen. That's the way you would ordinarily find hydrogen. So their numbers, even though they're nice enough to give it to you, you should have realized that they're zeros. How much energy does it take to form nitrogen gas from nitrogen gas? 0. Same thing with hydrogen. So this is 0 and 3 times 0. So basically all I have for this first one is 2 times 45.9. So this reaction that I'm interested in is exothermic. It's going to give off energy. Okay, what about delta G? Well, delta G, go look up in the table. Here's the value for delta G for ammonia. Slightly negative. I need 2 times it because 2 times the products minus this reactant and this reactant, but they're all zeros, just like they were before. That's those 4 zeros. These 2 were for the first one. These 2 are for the delta G's. So 2 times negative 16 gives me negative 32. So what did I learn about my reaction so far? Under standard conditions, okay? Now we're doing a gas phase reaction, so I should talk about partial pressures. If I had a container at 298 degrees Celsius, which is 25 degrees, okay? And in that container, I had 2 atmospheres of pressure, 1 atmosphere of pressure of ammonia, 1 atmosphere of pressure of hydrogen, and 1 atmosphere of pressure of nitrogen, and I had that all in a container at 25 degrees, I would expect that reaction to start to occur, right? That reaction would go to the right as written. How do I know that? Because delta G is negative. This is a spontaneous reaction as written under those conditions at 298 because these tables are at 298. Okay, second thing, this reaction is also exothermic, right? It's going to give off heat, so I'd expect it to liberate some heat as I go on. Okay, last thing, let's calculate delta S. Well, delta S, none of the values are 0. I need 2 times the number for ammonia, so 2 times 193, sorry, right here. See if I can get it all on the same sheet. There you go. All right, 2 times 193. Subtract off, be careful, put brackets around this whole part. What's this? This is delta S is products minus reactants. So I need 3 times the value for hydrogen plus 1 times the value for nitrogen. There's the nitrogen number. Sum this up first. Do this part first. 3 times 130.6 plus 191.5. Get that? Subtract that from 2 times this. You get negative 197.3. So this reaction, although it's exothermic and spontaneous, this reaction has an entropy, right, that is negative. That means it's going against nature. Why? Because I have 4 moles of gas going to 2 moles of gas. So you could have predicted its sign. You can't get its number, but you could predict its sign. To get its number, you use the tables, just like we did. All right, so what is that saying? Even though this reaction is spontaneous right now, at standard conditions, I can turn it around by raising the temperature because I want to do this normally under cold conditions because I want to minimize entropy's effect and maximize enthalpy's effect. So if I heat it up, I can get it to go non-spontaneous because this guy is negative in the Gibbs-Helmholtz equation will turn around the overall delta G, right? Because a negative times a negative will be a positive, and so delta G will start to become more and more positive as I go higher. So the delta S part will beat the delta H part at high temperature. So if you want this reaction to go and you want to be in the ammonia business, keep your vessel cold. Do it under very cold conditions. Okay, last question. Calculate delta G0 using the Gibbs equation. Well, delta G0 for our reaction is equal to delta G0, delta H0 minus T delta S. We're doing it at 298, so all I have to do is plug in my numbers from here, right? So again, since we're doing it at standard condition, keep my little 0. Here's my 91.8, don't do anything to it. Here's 298.15, that's the temperature. Be careful, why is this 0.1973? Because I need to move the decimal place over to get this to kilojoules, so it matches up with that. Most of the time, honestly, I change this one to match up with this one so I get to work with big numbers. But this case, I chose to do it the other way. So 298 times 0.1973 kilojoules per Kelvin, per mole Kelvin. This times this will add up to 58.8. So you see, entropy, the entropy term, after I multiply by T, is going to take away from the exothermicity. So delta G is going to be negative 33, right? So that guy's hurting that guy. Well, look what I got, negative 33 here. When I did it from the tables, I got negative 32. That's pretty good, okay? So they should match up. If you wanted to figure out what temperature you'd have to go to get this reaction to stop occurring, right? It's spontaneous right now, but if I want it to stop occurring, since both of them are negative, right? Delta G, since both of them are negative, I have to go to high temperatures to get it to stop. Right now, it's spontaneous. So what do? I set my delta G0 equal to 0 like we did in the last case. Solve for T, right? If I solve for T, what happens? Delta minus T delta S would go over to the other side. Then I divide both sides by delta S and I get T is equal to delta H for the reaction over delta S for the reaction. So opposite to the last one, we got two negatives. That's great. They're going to cancel out. Be careful with my delta S. When I take it from over here, when I take my delta S from over here, I need to get it in the right units. So I move this guy to kilojoules. Okay, that's the guy that I moved. Okay, either one, you've got to make this one either joules or this one in kilojoules. They don't naturally match up initially. So the two negatives cancel out. What temperature do I have to go to make this reaction become non-spontaneous? It's spontaneous at 298. But if I raise it, 298 Kelvin, but if I raise it to 465, this divided by this comes out to 465. Everything cancels except the Kelvin. At 465 Kelvin, this reaction will go to equilibrium. At temperatures higher than 465, I can make it go non-spontaneous. What's 465? If I change that to Celsius, that's 192. So 465 minus 273 will give you 192. At temperatures above 192 degrees Celsius, the reaction becomes non-spontaneous. Okay? A negative entropy factor takes over at 198 degrees. This guy becomes more important than that guy. Let's read this little note up here at the top. At what temperature will this reaction become spontaneous? It's going to become non-spontaneous at high temperatures. That's the situation when you have both of these negative, exothermic but more order. Got to go to high temperatures to minimize this guy. Okay, to maximize this guy because we want it to stop occurring. Right. This is the case where we want to become non-spontaneous. High temperatures, I can get it to turn around. Okay, that I believe is it for chapter 19. Thank you guys. Talk to you next time.